and start focus mode. Okay, let me share my screen. So today we are going to continue to talk about the sun, and we're going to talk about the nuclear fusions. First, there was a request to review the question from last class, one of the review questions from last class that was about, now this one. There was a question I posed last time. You can see my screen, right? So that two stars A and B have the same temperature. Star A has a larger radius than star B. Which of the following statements is correct? And this question turns out to be really hard, and you were evenly split in the answers. So I want to explain a little bit more what this really is about. It's about the Stefan-Boltzmann law of thermal radiation. What the Stefan-Boltzmann law says is that the total light output per unit area of an object increases with temperature. So that previously we talked about that the peak of this black body radiation shifts towards shorter wavelengths as you go hotter. So that if you have a hotter star, the radiation will peak at the bluer wavelengths, and then you have redder star, it will peak at the redder wavelengths. So the peak changes with temperature inversely, but the amount of output, this intensity of the light also changes with temperature. And you may notice that in these three curves, the hot stars curve is above the yellow star curve at everywhere, at all the wavelengths, right? Even if you will compare them at the fixed wavelengths, the blue curve is always above the yellow curve. And the yellow curve is above the red curve. What this means is that the intensity of the light also changes with temperature. And that is what the Stefan-Boltzmann law says. The intensity is increasing with temperature to the fourth power. So basically, if your temperature doubles, then the intensity of light is going to be increasing by 16-fold, by increasing by a factor of 16. And so that the bluer star will have a much higher energy flux than the redder star. When we say energy flux, it is the amount of light that come out per unit area on the star. So if you have two stars that have the same size, for example, if their sizes were the same, and the blue star, every unit area, it will be brighter than the red star. So overall, the star will be much more luminous, and we say that the total amount of luminosity will be higher than the red star. That is assuming when they were the same. The luminosity, when we say the luminosity, I guess I don't have that terminology on this slide, but the luminosity means the total amount of output given out by the star from all of its surface areas. Okay, when we say luminosity, that's the total amount of output from all the surface area. When we say the energy flux, it is per unit area. So that the energy flux is that you cut out a square meter on the star, and that is how much light come out of that area. That is the energy flux per unit area. And you want to know the total luminosity, you need to take this intensity, the output intensity at per unit area, and multiply that with the whole surface area of the star. And so if two stars have the same temperature, as it says in this question, that they have the same temperature, that means that the energy flux per unit area is the same, right? So that basically the intensity of light coming out of each square centimeter of the star is the same. But the star A has a larger radius than star B. That means it has a larger surface area than star B. And so then we can see which of the following statements is correct. If it has a larger surface area, then it is going to have a larger luminosity. When we say luminosity, when we say this word luminosity, that star A will have a larger luminosity. So option A is not correct because it says it has the same luminosity, because the luminosity not only relates with the temperature, but also relates with the size of the star. And that's so that this is not correct. And option B says B should have a smaller luminosity. That's correct. but the reason was wrong. The reason it was not because it has somewhat smaller flux per unit area. It is actually because star B have a smaller surface area. And so option C is correct because not only it compares the two luminosities in the right way, A is larger luminosity, but also it has a larger, but also gives the correct reason because it has a larger surface area. And then D is irrelevant. I hope that explanation explains that. So today we're going to talk about the sun, and then we're going to start with some review questions. And I'm going to start the question here and show it in, and also do it here. And you can see this close. Sunspots appear dark because they are they holes in the photosphere, so which you can see deeply into the interior of the sun, or is it a bit cooler and thus dimmer than the rest of the photosphere, or opaque structure, or is it causing eye damage? Okay, most of you answered and most of you got it correct. The correct answer is B. It's a bit cooler and thus dimmer than the rest of the photosphere. So this is also because of Stefan-Bollmann law, right? Because it's cooler, so that per unit area, the intensity of light the flux is lower. So it will look dimmer than the rest of the photosphere. So this was actually due to the same physical law I just explained. Next question. How is aurora produced? Is it an increasing the luminosity of the sun leads to light at night, or is it magnetic field turbulence or energetic particles colliding with things in the atmosphere? Okay, I'll end the poll now and share this with you. And it's not magnetic field turbulence. The correct answer is C. It's because of the energetic particles that are coming from the sun entering the Earth's atmosphere, and they collide and excite atoms in the atmosphere. And when the excited atoms return to ground state, they emit light. Sometimes when there's very strong solar activities, such as coronal mass ejections, that the Earth's magnetic field can get turbulent, that the solar activity can disrupt the magnetic field on Earth. But that is not the cause of the aurora. That can happen at the same time as you see auroras. You see aurora much more frequently than the chance of the Earth's magnetic field gets disrupted. Geomagnetic storm, we talked about last time, that can happen, but it's a very rare event. But aurora is much more frequent thing. They're both related with solar activities. It's just that the geomagnetic storm only happens when the solar activity is so bad that the Earth's magnetic shield got broken, basically. Next one, aurora location. This one should be easy. Why does aurora occur only near the poles? Because time is limited, I'm going to cut this short because this seems to be an easy question. All of you got it. All of you who have answered got it correct. It's the first one. Sorry to cut it short, but we are short on time. Next one. So I will just make a quick explanation that the reason that they only near the pole is because the field lines are perpendicular, so that the solar particles can get into the Earth's atmosphere. So what we learned from last lecture is that the semi-physical law that governs solar activity on the sun also governs the production of auroras. It's all because of the interaction between plasma and magnetic field. Next one, which of the following observation makes the best prediction about the chance of seeing aurora in the next few days? Okay, I have to end it now. It's been a minute. So not everyone answered, but the majority of you got it right. And the correct answer is B, is a coronal mass ejection on the sun. When that happens, a lot of energetic particles get released by the sun and pushed into the space, ejected into space, right? It's a mass ejection that ejects a lot of these energetic particles. And when those particles come to Earth, they can produce auroras. I mean, the sun actually is doing that all the time. Is giving out solar wind all the time, so that we see auroras quite often. So you see that a lot. But when coronal mass ejection happens, auroras will be particularly beautiful. It will be much, much stronger than usual. And these other things, three of the other options, I mean, the total solar eclipse has nothing to do with auroras. This is just we got into the moon's shadow. And sunspot is a solar activity, but it's not a very strong kind of solar activity. And stable prominences also happens a lot on the sun. It's usually related with sunspot, and it's also kind of a low level activity of the sun, not as strong as a coronal mass ejection. So this is the best prediction for seeing strong auroras in the next few days. Okay, that's all. Pose. So today we're going to talk about nuclear fusion in the sun, and the sun is shining because of nuclear fusion of hydrogen into helium in its core, and it's giving us huge amount of luminosity, and that luminosity can be again calculated using the Stefan-Boltzmann law and the sun's radius, because the Stefan-Boltzmann law says that the amount of energy flux per unit area is proportional to temperature, right? So you multiply the flux per unit area with the total surface area, that gives you the total luminosity. And that is a very large number, and it's about equivalent of 100 billion atomic bombs every second. So you imagine 100 billion atomic bombs every second. A billion is a pretty big number, right? This is 10 to the 9th power, and this is 10 to the 11th power. So that many atomic bombs every second, that is how much the sun gave out every second. And that is a huge amount of energy. And we don't get all of that energy. We only get a tiny fraction of that energy because we're so far away from the sun, and the sun's luminosity is radiated in all the directions, right? Not only in the direction towards the Earth, and also in the direction towards the empty space out there. So that all the other directions, every direction gets the same amount of energy. And our Earth covers an only tiny fraction of the sky. You're looking at it from the sun, right? So you're looking at the Earth from the sun, it's a tiny grain of rice, right? And remember that it's like 25 meters away if the sun was shrunk to a basketball. So the Earth covers a tiny area. And so we only get a tiny fraction of that luminosity. But still, even that is quite a lot. That is powers all our daily activities, basically, that all the energy sources that we are using are originally come from the sun. And suppose that we can actually capture the sun's energy in all the directions, then we actually don't need very much. We only need to store 1 second's worth of the sun's luminosity. Remember, the luminosity is, again, the energy in all the directions, right? From the whole surface area. And so if you are able to store 1 second of the total luminosity, we could meet humanity's energy needs for the next 500,000 years. But we don't have that technology now, and it's going to be far in the future that one day we may be able to do that. So what powers the sun? What gives us much energy? We now know it is nuclear fusion, but how do we know? In ancient times, we actually didn't know it was powered by nuclear fusion. We only got to know this in the past 100 years. And before that, I mean, no one knew what powers the sun. And in the old times, people thought maybe the sun is just burning coals. It's that because at that time human can produce fire on Earth, and they do that by burning wood. And then later on, when we find coal, that we found it's very good, and we can burn coal to produce fire. And then we see, okay, the sun seems like a really bright thing in the sky. It's probably a big fireball, and maybe it is just burning coal. Why couldn't this assumption be correct? Why isn't burning coal not a possible energy source for the sun? So we want to go through this reasoning. So how can we check if this assumption works or not? The assumption is that the sun is burning coal, but how do you prove that is not the right theory for the sun's energy production? How do we check this? How do we check if an energy source can work or not? In order to do that, we need to see how long it can last at the current rate of consumption. Basically, the sun is giving out energy every second, and you need to see how much total energy it has, and then see how fast it is using it. And then you can know whether it will last a long time or not, because we know the sun has been shining forever, almost, not forever, but it's for a long time. And so this argument is like if you have $1,000 in a bank and you use $100 every day, how long can your deposit last? How do you figure that out? You just take the total amount of money you have, divide that by how much money you use every day, right? So you take $1,000 and divide by $100 every day. That means this $1,000 can last for 10 days. Suppose you don't bring in more money. And so this is the same argument that we're going to use to evaluate whether coal burning sun could work or not. So there are two facts that we have to use. That one is that the sun gives out a huge amount of energy every second. And we know that. We know how much, we can measure how bright the sun is, and we can figure out how much energy the sun gave out every second. And we also know it has been shining like this for a very, very long time, for billions of years, right? So that if we see that if the sun is made of coal, can it last for this long? We know the luminosity is 4 times 10 to the 26 watts, and that is 4 times 10 to 26 joules per second. We know the sun has a mass of 2 times 10 to 30 kilogram. I'm going to go through the mass for you so that you can see how the argument is made. So suppose the sun is made of coal, and each kilogram of coal can produce at most 3.5 times 10 to the 7 joules of energy, about 35 million joules of energy. So that's a kilogram of coal. It's a lot of energy, yeah. And if suppose the sun is completely made out of coal, how much energy could it produce in total if you burn the whole sun, right? And that is 2 times 10 to 30, the mass times the amount of energy per kilogram. And so you get the total amount of energy that the sun could produce if you burn the whole thing. And then so basically this is the total amount of money you have in the bank. And now you need to divide it by the rate of consumption. It's basically how much money do you spend every day? I mean, the sun spends about 4 times 10 to 26 joules per second because it's giving out that much light. So you divide the total amount by the rate of consumption, you find out it's about this number, and that is about 5,000 years. That is not a very long time, right? 5,000 years is very short. If the sun were burning coals, if its luminosity is produced by burning coal, and if the whole sun was made by coal, it could have only lasted for 5,000 years. So that's obviously cannot be correct. Is that the sun couldn't last this long it couldn't last longer than 5,000 years. But we know that our human civilization has been more than 5,000 years, and Egyptians built the pyramids. Almost 10,000 years ago, and so that was it cannot be true. And if you say, okay, maybe it's not coal, it's something else. If it's oil, it's also not much longer. It would just be 7,000 years. So these things obviously cannot be correct. The sun cannot be made by burning coals. What about other possibilities? So another possibility is that smart people brought up in the 1800s, that they said that maybe the sun is shining by converting gravitational potential energy to radiative energy. Is that if the sun is actually contracting little by little, then the surface layers of the sun is actually falling toward the center, right? If you know that when things fall, their gravitational potential energy gets converted to kinetic energy or some other form, right? If you have a stone drop from the mountain, when it reaches the ground, it will have very high velocity, and maybe that energy can be converted to light, and maybe the sun is doing that. Maybe the sun is just contracting a little bit, and every layer of it falls a little toward the center, and that will release some gravitational potential energy, and maybe that is enough to power the solar luminosity. And then you can actually do the calculation here. You don't have to understand this math, but this is expression for the gravitational potential energy for a spherical object. And if you change the radius of it, that will give you a net amount of energy, so that if the current radius is smaller than the original radius, it will give you a net amount of energy. And that net amount of energy, if you convert that to light, you can actually power a lot of light. And given the sun's current size, it could have released at most 3.1 times 10 to the 41 joules of energy. And so is this enough? Is this enough to power the sun for billions of years? So we can try to see whether that's correct. We just, again, take the total amount that is available divided by the rate of consumption. And then you get the answer, and we found the answer is about 25 million years. That's much longer than burning coals, right? As burning coals is only 5,000 years, and this is 25 million. And so it's much longer. But it's 25 million years long enough. And dinosaur size, that cannot be right. I was there more than 25 million years ago. We know that from study of fossils and geology, we know that the dinosaurs first appeared on Earth about 234 million years ago. And our liquid ocean has existed on Earth for at least 3 billion years. So that if the sun was just doing gravitational contraction and turning that energy into light, that's still not enough. It is not enough to power the solar luminosity for billions of years. So the sun cannot be powered by gravitational contraction either. So these arguments shows that basically, first of all, how you rule out hypotheses. And then it shows that the sun cannot be powered by burning coal or gravitational contraction. So what power could it be? It has to be something else. And before Einstein, we didn't know what that could be. And after Einstein's general relativity, we understand mass can be converted into energy. If you convert a little bit of mass into energy, and it's actually, if you just use a tiny bit of mass, you can produce a lot of energy because E equals mass times speed of light squared. And speed of light is a very large number, so that if you just convert a tiny bit of mass into energy, you get a lot. And if this is a possible way to work, then it will be able to power the sun for very long. And how much mass do we really need to power the sun for 10 billion years? Here, we don't need the whole sun anymore. We only need a tiny bit of the sun. We only need like less than 1%, like less than 0.1%. We only need about 0.07% of the sun's mass. We just convert the tiny fraction of the sun's mass into energy. That is sufficient to power the sun for about 10 billion years. This is actually the expected lifetime of the sun. That is right now the sun is about 5 billion years old. It has 5 billion more years to go before it some events will happen to it, and it'll die die in a star's way. But its total lifetime is going to be 10 billion years. So, but we only need a tiny fraction of its mass to be converted to energy to power this huge luminosity of the sun for this long periods of time. So only nuclear fusion can produce enough energy to power this huge luminosity for its long lifetime. And we don't need much. We only need the 0.07% to power it for 10 billion years. So what I want to talk next is to show you that what kind of condition is needed for fusion. And then in the rest of the chapter, we will talk about what is gravitational equilibrium and energy balance, and what is the direct evidence for fusion, and how is stable fusion really maintained, and understand how the fusion energy is transported outward. You may not know all of these throughout this chapter, but we will cover some of these topics in the future when we talk about stars as well. So what is nuclear fusion? Nuclear fusion is that you put two light elements together and they make a heavy element. And in that process, a small amount of mass gets converted to energy. And that same process is at work in the sun is also what powers a hydrogen bomb. Not an atomic bomb, right? Atomic bomb and hydrogen bombs are different. A hydrogen bomb is actually doing the same thing as what's happening in the center of the sun. But hydrogen bomb, of course, it's much weaker than the sun itself. The sun generates about 4 times 10 to the 26 joules, but a hydrogen bomb is only about 5 times 10 to the 16 joules. So the difference is about 10 billion. The sun is like 10 billion hydrogen bombs every second. And so that is a big difference. But the first question we want to understand is what condition is required for nuclear fusion? And to understand this, we have to first look at the nuclei, because it's nuclear fusion. It's a reaction in the nuclei of atoms. In the nuclei of atoms, we have protons and neutrons. For example, in the helium nucleus, you have 2 protons and 2 neutrons. The protons have positive charge, and the neutrons have neutral charge. Neutrons have no charge, not positive nor negative. In the helium nucleus, you have 2 positively charged protons. The positive charge, they should repel each other for electric force, right? Because the same charge will repel and opposite charge will attract, right? So that because that it's 2 positive charges, in principle, they should repel each other. How can the protons stay together? How can these 2 protons stick together? Why didn't they push each other apart? Because the repulsive electromagnetic force between them, electric force between them is repulsive, right? They should push each other apart. How can they stay together? And the reason they stay together is because there's a new kind of force that is at work. And that kind of force is called the strong force. It's one of the 4 fundamental forces in nature. And we don't experience this kind of force in our daily lives because it doesn't apply to large scales. This kind of force can only be detected or felt on very, very small scales in the size of a nucleus of an atom. In the nucleus of an atom, it's a very, very tiny scale, right? It's remember the Power of 10 movie, and that the nucleus of atoms are tiny. And on that tiny scales, a new type of attractive force called the strong force can hold the protons and neutrons together. And it's why we call it strong force, because it's even stronger than the electric force between protons. The electric force between protons is trying to push them apart, but it's not as strong as the attractive strong force between them. So that's how the 2 protons can be held together. But it only applies on very small scales. It's on the scale of the nucleus. So the question that we want to evaluate is that if 2 protons inside the star are on a collision path towards each other, if you say I have 1 proton here and 1 proton there, and they're trying to come together to form a helium nucleus, can they do that? What kind of force do they feel? Right? They can feel gravitational force, they can feel electric force between them, which is repulsive. They can also feel the strong force that is attractive. Which one affects them most? On large scales, the only force that will affect them are the gravitational force and the electromagnetic force. But the gravitational force is much weaker compared to the electromagnetic force, so it is not relevant here. That the first thing that the force that is dominating the process when the 2 protons are at large distance is the electric force between them, and that is a repulsive force because they have the same charge. So if 2 protons are on the collision course, what fundamental forces affect the most is at first it's the electric force. The strong force is only stronger than electric force on small scales. It's not stronger on large scales. It's very weak. They don't feel the strong force until they come really, really close to each other. The electric force is what dominating the force they feel at large distances. And this force is very repulsive. It's trying to push them apart, and it will become stronger as the 2 nuclei get closer. So it actually prevent these 2 things to get very close. And the strong force, although the strong force is attractive, but it only apply at very close range. So we want to use this potential diagram to show you what it's like, right? the potential diagram for the electric force is like a mountain. That you're trying to push two positive charges together, that the closer they get, the stronger of repulsive force they would feel. So that the harder it will get to push these two things together. So that if you give them two initial velocities and have them run towards each other, it's like they're running towards this peak of the mountain from two sides. And then the closer they get, the larger a tendency that they get pushed apart, right? The larger force that is pushing them apart. So that if there's only electric force around, then these two protons will never get together, because when they get really close, the force that's pushing them way apart also get really, really strong, and that can reach infinity. And so that means these two protons will get pushed apart again, no matter how fast you let them run towards each other. But for an attractive force, like a strong force, what the potential well will look like. If it's an attractive force, then the potential well will look like a well in the middle. You have two things that is running towards each other. Maybe initially they're coming towards each other at very slow speed, but the closer they get, the stronger an attractive force they would feel, and so they will fall into the well together. And that is the potential for an attractive force. Then what will be the combination of the two? If we combine the electric force and the strong force, the potential diagram will look like this. That initially, when you're trying to push these two things apart, they feel like it's a mountain, that it's getting harder and harder to get closer to each other. But then once they cross a certain threshold, they will feel this strong attractive force, and then they will fall into this well. So this is the combined potential diagram for the electric and strong force. So that initially they were feeling this repulsion between each other, the electric force trying to push it apart. But then when they get close enough, they would overcome the electric repulsion, and then start feeling the attractive force and go towards each other, go together. So how can the protons get close enough together? How can the electric repulsion be overcome? Any ideas? I need some quick response if you have some idea. How can we push the two things close enough so that they feel this attractive force? No response? You have to push them very far, very fast, right? If they come with very high velocities, they will be able to go over the threshold and start feeling the attractive force, right? If they don't go very fast, they will not get close enough, right? The faster they go, then the closer they would get before they get turned around, right? So remember that before, if you only feel the electric force, then the gravitational potential is just going up like infinity. And you're trying to push these two things together. You start with some slow speed, they'll stop and then turn around. But if you go with a faster speed, they'll get closer before they get turned around. And if you keep increasing the velocity, they'll get really close before they get turned around, right? So if the point where they stop and get turned around is smaller than this range, when they can start feeling the attractive strong force, then they would overcome the repulsive force and start feeling the strong force and come together. So that they have to run toward each other with very high speed. So under what circumstances would the nuclei be moving at a very high speed? Any reactions? Gravity? Temperature? Yes, temperature. High temperature is what is needed for the nuclei to be moving at a very high speed, because temperature is a measure of the average kinetic energy of each gas particles. That if you have, when you heat up the water, for example, the atoms in the water actually move faster. And when you heat up a gas, we get the gas particles are also moving faster inside. And higher temperatures means faster moving particles. And so that if you make the temperature really, really high, then the protons will be moving at very high speed. So there's some chance for them to get close enough to overcome the repulsive force and start feeling the strong force to come together. So the condition for nuclear fusion is that you need very, very high temperature. At low temperature, they get turned around very quickly, and before they can get close, you increase the temperature, they can get closer, but maybe not yet reaching the threshold until they can feel the strong force. But if you go really high temperature, after you cross a certain threshold, this is possible for two protons that are colliding towards each other, that are moving toward each other to get close enough, and then they start feeling this attractive strong force, and they will come together. So you need a very high temperature, and there is a certain threshold for that. And for hydrogen to helium fusion, the minimum temperature is about 10 million Kelvin. 10 million Kelvin. That is a very hot temperature. We don't have that hot temperature on Earth. You can make that momentarily in a hydrogen bomb. And so that is how you can make a hydrogen bomb. And so if the gas temperature is high enough, it will be able to do this. And how fast are they moving when it is 10 million Kelvin? At this temperature, protons will have an average speed of about 450 kilometer per second. So that's really, really fast speed. And that will be fast enough to cross China from east to west in about 12 seconds. So that is how fast they will be moving at 10 million Kelvin. And that if they're moving at that speed and towards each other, they can overcome the repulsive force and fall into the well. So here is another question. Solar corona is very hot too. Some stars could have a corona hotter than 10 million Kelvin. Will we have fusion in a corona? Why wouldn't we have fusion in a corona? What is going on? Why don't we have, I mean, obviously we don't have nuclear fusion in the solar corona. Why wouldn't we have fusion in a solar corona? In principle, yes, but it almost never happens. Any reaction why that is the case? Not dense enough. That's right. It's not dense enough. Because the density in a corona is too low, it is unlikely for two protons to be on the path of collisions. Right? You have to have. I mean, the protons are running in all directions. Right? They don't always run towards each other. It's just run towards each other by chance. That in a corona, the density is so low that they will almost never run directly towards each other. So they'll miss each other, even if they were moving very fast. So you really need the density to be high enough for them to have a collision. Remember this thing we talked about at the very beginning of this class, that in which of the following situations is more likely to have a collision, in a crowd or in a baseball field, right? If these people are running around in random directions, right? Suppose these people are not just standing around and just running in random directions, then it's very easy for them to collide because the density is high. But here the density is too low. It almost never collide, even if they run randomly. So to have enough fusion to power the sun, we need very high density as well. So we not only need high temperature for them to move fast, but also we need high density to have enough protons that just by chance be on a collision course, that are moving directly toward each other. And then they can get close enough to form helium. And so where on the sun do we have both high temperature and high density? It is in the center of the sun. And because the The sun is hottest in the center, is also densest in the center. Why is that the case? So this actually shows you a cross section of the sun, and the left side shows you how the density increases from the surface to the center, and you can see the center is much denser than the surface. This curve on the right shows you the temperature change from the surface to the center, and the center is also very hot. Why is density and temperature much higher in the center? It's because of gravitational equilibrium. It's like, imagine this acrobat, that these three people stacked up on each other. This person at the bottom is under the most pressure, right? Because the gas in the center of the sun is like this guy, and is under most pressure, and you're pressing the gas towards each other, so that not only the density is high, and also the matters have to move faster in order to resist the strong gravitational force from above, because all the outer layers of the sun is trying to fall towards the center. And so the center has to be really dense and hot to resist that, to produce large pressure. Okay. So that's what I'm going to talk about today, and we can end here, and then I'll continue to discuss the process of fusion next time. That's it. Thank you very much for joining today's class. Yeah. Let me know if you have questions. I'll upload the PowerPoint. I'll try to do that soon, just in a few hours. Bye.